Okay, so to start off today, we want to take a look at values of our functions, our trig functions, outside of what we've been looking at so far. We've been focusing on right triangles. And there are two things we know about a right triangle. First of all, we know that the right angle is 90 degrees. So if I label this triangle ABC, sides little a, little b, little c. We also know that any triangle has an angle sum of 180 degrees. In other words, all three of those angles, angle A plus angle B plus angle C, has to be 180 degrees. Well, since angle C is already known to be 90 degrees, that tells us that angle A and B have to be complements or add up to 90 degrees. And it also tells us that each angle, not even equal, just greater than, A and B has to be between 90 and 0, or 0 and 90, however you want to word it. Degrees. That's why we've only focused on doing trig functions with angles that are between 0 and 90 degrees, because these angles are going to be between 0 and 90 degrees. But remember, these trig functions don't come from the triangle. They actually come from that unit circle. We have our unit circle, and we have our reference diameter there. And we typically put in that complementary reference diameter, and also that vertical reference diameter. And we've mentioned that if we have an angle here, let's put this in like this. Call that 30 degrees. This side of the angle here is what we call the terminal side. And where that terminal side ended on the circumference of our circle, the distance from that point down was the sine of our angle. Well, that 30 degrees is the angle here. That is a 30-degree angle. But in this case, 30 degrees... Oops, was there somebody have a question? That 30 degrees is also what we refer to as a reference angle. It is the angle between that terminal side and our reference diameter. Well, there are several other angles on this unit circle that are related to that 30-degree angle here. The first type of related angle we're going to talk about is called coterminal angles. What coterminal angles are is they're angles that have their terminal side in exactly the same spot. So we have that 30 degrees, but we could also have an angle that wraps all the way around once and then comes to 30 degrees. That would be 30 plus 360, or 390 degrees. So 390 degrees is coterminal with the 30 degrees. And note that its sine will be the same. If I go to the calculator and I type in the sine of 30 degrees, I get, oops, let me make sure my modes are set correctly here. Let's try that again. Sine of 30 degrees, I get 0.5. If I do the sine of 390 degrees, it also tells me 0.5. If I wrapped around twice, so 360, another 360 would be 720, and then another 30, so that's 30 plus 360, and another 360, that's 750 degrees. That's also coterminal. Its terminal side is at the exact same place as the 30 degrees and the 390 degrees. If I did sine of 750, we see, again, the sine is 0.5. So every time we go around, every 360 degrees, we can generate a coterminal angle that has the same terminal side as 30 degrees and therefore the same sine as 30 degrees. This is not very important as far as geometric applications, but we'll talk about where it comes into play in a little bit. Other related angles the angles with the same reference angle. So let's put that 30 degrees back on here again. Of course, its sine is right there, that 0.5. Well, there are other points on here that have a 30 degree reference angle. We could have a 30 degree angle here. That would be 30 degree reference angle. And guess what? If we followed this out, that sine is still 0.5. Well, what angle corresponds with that? Well, if we wrapped around from here, we see that it is the supplement of 30 degrees. This is a line here, so that line is 180 degrees. We have to subtract the 30 degrees, getting this to be 150 degrees. Oops. So our 180 minus our reference angle of 30 gave us that angle is 150 degrees. Note on the calculator, if we do sine of 150 degrees, the sine is still 0.5. They have the same angle. So supplementary angles have the same sine. That's very important for what we're going to do towards the end of class here today. Now there's also a 30 degree reference angle here. However, that sine is not 0.5, it goes down. It'll have a sine of a negative 0.5 because it's below the reference axis. Find that angle, well, it's the 180 degrees to here plus 30 degrees. That's 210 degrees is that angle. And if we double check it, sine of 210, it is a negative 0.5. Same reference angle, it's just below the axis instead of above it. And there's one final place over here where we have a 30 degree reference angle. Its sine should also be a negative 0.5. It's the same distance, same length, just below our reference axis. And that would be all the way around. It's just 30 degrees short of making the full circle, or 30 degrees short of 360. That'd be 360 minus 30 degrees is 330. And that'll be a negative 0.5. So let's test it out here. Sine of 330 is also a negative 0.5. So these angles have the same reference angle. They were 30 degrees, 150 degrees, 210 degrees, and 330 degrees. Had the same reference angle. These first two have the same sine. These second two have slightly different sine. It's the negative of that sine is all it is. For the cosine, a little different. So let's throw our 30 degree reference angle on here again. The cosine is this length here, this horizontal length over where that sine is. Remember, technically the cosine is the sine from the point where that angle hits the outside of the circle to the complementary reference diameter. So it'd be that way. But instead of drawing it in up there, we just draw it in down here because it'll be the same length. So that's our cosine of 30 degrees. Now we still have the same angles that have the same reference angle, but we'll notice that because of the way the cosine is situated, it's not this angle over here. It's not the 150 degrees that has the same cosine. It's the 330 degrees that has the same cosine. If I do cosine of 30 degrees, I should get 0.866. There it is. If I do cosine of 330 degrees, I will also get 0.866. These other ones over here, remember this was 150 and 210. They will be the opposite because they're going in the negative direction here, to the left of the center. Cosine of 150 is a negative 0.866. Cosine of 210 is also a negative 0.866. So we have those relationships. Typically, rather than referring to this as 330 degrees, because it's way closer to zero, to call it a negative 30 degrees, especially for a cosine, since that's where it's positive. The cosine of 30 degrees is equal to the cosine of negative 30 degrees. If I put that in as a negative 30 degrees, you see I get that positive 0.866. So the relationship we're seeing here is that if for an angle A, I'll just use the letter capital A instead of using theta. The sine of angle A is equal to the sine of its supplement, 180 minus angle A. So if you pick any number, let's say 71 degrees, its supplement, 180 minus 71 is 109 degrees. If I punch those in the calculator, sine of 71, I get 0.9455. Sine of 109, I get 0.9455. And for a cosine, the cosine of angle A is equal to the cosine of the negative angle A. So for 71 and negative 71 degrees. Now technically that would be 360 minus 71 would be 289 degrees, is another way to think of it. But if I do cosine of 71, I get 0.3256. Sine of negative 71, I get 0.3256. Or cosine of 289, same thing, 0.3256. So these are important relationships to keep in mind. Most important is going to be this one right here. It's going to bring us into our second topic of the day. What happens when we have triangles that have angles bigger than 90? Well, obviously it's not a right triangle because bigger than 90 degrees is an obtuse angle, and we know a right triangle cannot have any obtuse angles. The largest angle is that 90-degree right angle. It can't be anything bigger than that. So we must be looking at a triangle like this, or like this, with no right angles. So these triangles are called oblique. They're called oblique because they're not right. So if anybody ever calls you oblique, you know what they're hinting at. And in an oblique triangle, some rules to review some things that we've talked about a few weeks ago. if I have angles A, B, and C, now I tend to label the largest angle angle C just out of habit, but it doesn't always have to be. Let's say that this is 98 degrees. This one over here, let's make it 29 degrees. So that'd make this one 63 degrees. I have side little a, little b, and little c. I know that side little c here has to be the largest side because it's opposite the largest angle. And I know that side B here has to be the smallest side because it is opposite the smallest angle. Well, we use that relationship in our trig functions to find missing pieces of these oblique triangles, just like we did with right triangles. All triangles have 6 parts, 3 sides, and 3 angles. If we have 3 of those pieces, 3 out of the 6, we can find the others. The only exception is if what we're given is all 3 angles. If we're given all 3 of the angles, we're out of luck. We can't find the sides. We have to have at least one side. But the rest of what we have doesn't matter. Then if we have any 2 other parts, as long as we have at least that one side, we can find the other parts. And we saw that with our right triangles. Let's look at it with our oblique triangles. So I'm going to label this triangle A, B, and C. And again, sides little a, little b, and little c, where, of course, side little a is opposite angle big A, side little b is opposite angle big B, and C is across from angle C. The relationship between the length of the sides and the size of the angles is described with something called the law of sines. On that unit circle, as the angle gets larger, the sine gets larger. So bigger angles have bigger sines. We saw before that the length of the opposite side is related to the angle. The biggest angle is across from the largest side. The smallest side is across from the smallest angle, and so on. So this gives us the relationship that the length of side A divided by the sine of angle A is the same ratio as the length of side B divided by the sine of angle B, which is also the same ratio the length of side C divided by the sine of angle C. This is the version of the law of sines that I learned and that I have used in my life. Now, some textbooks might show it like this: sine A over sine of angle A over the length of side A, sine of angle B over the length of side B, sine of angle C over the length of side C. This is the exact same rule, they just flipped it over. The ratios, the calculation is still going to work out exactly the same. So whichever way you're used to doing it, whether you put the sine on top, the sine of the angle on top, or the length of the side on top, as long as you're consistent and do it the exact same way every time, you're still going to get the same answer. So let's take a peek at how this works. One requirement here. We must have one pair where we have the angle and the opposite side. So over on this triangle, let's call this 81 degrees. I'm just going to label it A, B, and C. We'll call this angle over here 56 degrees. We're looking for side A, side B, side C. Let's say that I'll give you that side A is 27 feet. I need to find angle C, side little c, and side little b. Let's start out by finding angle C here. Angle C is pretty easy to find because we can use our angle sum of a triangle. 180 degrees minus 81 degrees minus another 56 degrees gives us, what is that, 43 degrees is angle C. Angle C is 43 degrees. That was pretty simple. That really didn't involve trig. That was just basic geometry. Define sides B and C. Let's do side B first here. That's going to use the given information. I need that pair where I have the angle and its opposite side. That's right here. I have angle A is 81 degrees, and its opposite side, little a, is 27 feet. So I have 27 feet over the sine of 81 degrees. That's the beginning of my ratio, or my proportion. On the other side, I need the piece of information for what I'm trying to find. If I'm trying to find side B here, well, B is the length of the side. That'll go on top since I put the length of the side on top over here. And it's going to go over the sine of the angle that would go with that is the 56 degrees. And now this is a proportion. It is simply cross, multiply, and divide. So we have 27 times sine of 56 degrees. Make sure we close that parentheses before we divide. Then we'll divide by the sine of 81 degrees. Close that parentheses. We get 22.66. B is 22.66 feet. Now we can stop here for just a second, or pause for just a second, and analyze. Does that make sense? Well, yes. B is 56 degrees compared to 81 degrees for A. The opposite side from the 81 degrees is 27. The 22.6 is opposite the 56 degrees. It's a smaller angle. Opposite it is a smaller side. So that makes sense. I mean, it doesn't prove we did it right, but it'll stop us from some major mistakes. So that 22.66 is side B. To find side C, we go back to that same ratio, 27 feet for side A over the sine of 81 degrees for angle A. We're looking for side C, so that has to go on top because we're putting the length of the side on top here. The angle across from it is the 43 degrees. Now here we've said we try to avoid using something that we calculated ourselves. Here we don't have a choice. That's all there is for us to use. So now we're going to cross multiply and divide here. It'll be 27 times sine of 43 divided by the sine of 81. Again, making sure you close your parentheses on your sines. I get 18.64. So again, let's take a peek at this. That is my shortest side. It is opposite my smallest angle. That makes sense. Longest side is opposite my longest angle. So those things match up. Again, it doesn't catch every mistake, but it catches some really bad ones. We at least know we've got things in the right order as far as magnitude. So here was a case where we were given an angle and the length of its opposite side. That's what we need to be able to do this law of sines. But there are a couple other possibilities that we can run into. We might be given two angles and a side that is not opposite either one of them. It might look something like this. So this might be 78 degrees. Label this A, B, and C again. This one down here might be 51 degrees. And we are given that side little a, little b, little c. We're given that side little c is 140 feet. We need to find angle C at side A and side B. So here we were given two angles and a side, just like we were up here. Up here we were given two angles and a side, but up here the side we were given was opposite one of our two angles we were given. Here the side we're given is not opposite one of the two angles we're given. Fortunately, because of what we've seen several times, the angle sum of a triangle adds up to 180 degrees. We can find angle C really quickly. 180 degrees minus 78 degrees minus 51 degrees gives us, shoot, that's not how I wanted that to work out, 51 degrees. So angle C up here is 51 degrees. This is an isosceles triangle. Not what I was shooting for, but that works. That being 51 degrees, we can now find, of course, we know that side B better be the same length. That's going to be 140 feet because those two angles are the same. Their two opposite sides better be the same. But let's find side A. So we have the 140 feet, and its opposite angle is the 51 degrees. And I'm going with side C just because, and angle C just because that's the first one I looked at. It's the same. Of course, side B is also 140 feet, and angle B is also 51 degrees. So you could think of as being either one, really, if you wanted to. We are trying to find now side A. That goes on top with our 140 feet, because that's the length of a side, over the sine of 78 degrees. Now, since that angle 78 degrees is bigger than 51 degrees, we're expecting A here to be larger than 140 feet. So we're going to cross, multiply, and divide. The 140 times sine of 78 divided by sine of 51. We get 176.21 feet. That makes sense. It is longer than the 140 feet, and it is across from the largest angle. Now that one turned out to be an isosceles triangle, but it really doesn't matter. It's the same concept holds. It's still oblique, still no right angles. And what we find is anytime we are given two angles and one side, we can solve that triangle using the law of sines. Because anytime we're given two of the angles, we're basically given all three angles, and we can find the third one really quickly using that angle sum. So anytime we have two angles in one side, we're good to use the law of sines. It's the same process. It gets a little more complex if it's the other way around. If we're given two sides and one angle, there are a couple of possibilities here. My first possibility is the angle is between the two sides. I'll draw this out, show you what it means, show what it looks like. So I have angles ABC, sides little a, little b, little c. If I tell you that side C, or side B is 48 feet, and side C is 63 feet, and that angle A here is 57 degrees, this angle A here, being between our two given sides, is called the included angle. It's because it's between the two sides. It's included between the two sides that we're given. You'll notice here that we do not have an angle and its opposite side. We only have one angle, so we cannot find the other angles here. We cannot use the law of sines. Instead, we'll use what we're going to talk about on Monday, or one of the things we'll talk about on Monday, the law of cosines. In fact, this right here is one of the two cases where we use the law of cosines. All the other cases we use law of sines, but this is one of the two places where we would use law of cosines, where we have two sides and that included angle that's between them. So we can't do this example here. The other example we have is where we have two sides and one angle opposite one of the sides. Now, however, here, we've got to be careful. There's two possibilities here. The angle is opposite the longer side. Let me show you what I mean here. I'm going to give you angles A, B, and C, sides little a, little b, and little c. And I'm going to tell you that I have angle A here is 47 degrees. Side A, the opposite side, is 43 feet. Side B is 29 feet. The angle is opposite the longer side. 47 degrees is opposite the 43-foot side. That's the longer of the two sides that are given. The reason this is important is there's only one possible triangle I can construct from this information. Here's side B at 29 feet. Right? Angle A will be over here somewhere. 47 degrees is going to come off like this. Well, there is only one way that we can draw in the 43-foot side here. We have to go like this, way past, and we'll draw this 43-foot side back in here. Actually, let me do this, so I don't run off the page so bad. There's my 29-foot side. My 43-foot side actually comes back something like this. This is 43 feet. So here's angle B. This will be side, angle C, side little c. We can find these pieces. So to find angle B here, to find that missing angle, it's a little more work. As you're probably figuring out, when we have two angles and a side, that's the easy case, those first examples. But when we have two sides and an angle, it gets to be a lot more complicated. We have the case we looked at before where we couldn't solve it. We're going to have to use a different rule to use that. Here, we can solve it because the longer side is opposite our angle that's given. But the calculation is a little tougher. So we have the 43 feet that is across from our 47 degrees. So it's over sine of 47 degrees. Equals, the only other piece of information we have is the 29 feet. So that's going to go on top because that's the length of our sides are going on top. And the angle across from it is angle B. So this will be sine of B down here. Now when I cross multiply and divide, I am not going to get angle B. What I'm going to get is the sine of angle B. If I do the sine, 47 degrees, times 29 divided by 43. I get 0.4932. Now you'll notice I did not clear my calculator. I left it in the calculator. Because to get angle B, I have to do another step. If I know the value of the trig function and I want to figure out how big the angle is, I do the inverse trig function. This will be the inverse sine of 0.4932. Now, if I just wrote down 0.4932 and typed it back in, there's a huge round off error there. So I'm just going to do this. I'm going to do inverse sine, and then I'm going to do second answer, telling my calculator to use that previous answer, the 0.4932385543. It actually keeps going on and on. I hit enter, and I get 29.55 degrees. So that's telling me angle B is 29.55 degrees. Angle C can then be found using 180 degrees minus 47 degrees and minus the 29.55 degrees. Minus 47, that's 133. This is 103.45 degrees. So we found angle C. Angle C is obviously obtuse here. We can now find side C by, again, doing our law of sines. So I'm going to do, it's still the 43 over the sine of 47 degrees. Side C is what we're trying to find. Over the sine of angle C, we have to use the angle we calculated here, no way around it, 103.45 degrees. So again, we'll cross, multiply, and divide. But here we're back to finding a side, so it's the same as what we were doing in those first couple of examples. So 43 times the sine of 103.45, close that parentheses, divided by the sine of 47 degrees, gives us 57.18 feet. So side C over here is 57. 0.18 feet. The reason that worked is because the angle is opposite the longer of the two sides that were given. Well, what happens if the angle is opposite the shorter of the two sides? The angle is opposite the shorter of our two sides. So I'll give you angles A, B, and C again. Let me tell you that angle A is 29 degrees. Its opposite side is 18 feet, and B's opposite side is 40 feet. So, actually, let's do this. Let's make this, just to be on the safe side, we're going to make that 21 feet for side A. So we've got angle A is 29 degrees, side A is 21 feet, side B is 40 feet. So what this means is when we go to draw this triangle, I'm going to put side B down here first of 40 feet. Angle A here is 29 degrees. The reason there's an issue with the opposite side, the side opposite our angle being the shorter side, is it's ambiguous. I could put that 21 feet right here, or I could extend this side past here, and there's a spot over here that this would also be 21 feet. How do I know which triangle it is? I don't. There are going to be two possibilities for angle B here. So in order to be able to solve this triangle, I need to know, is B obtuse or acute? If I tell you that B is acute, then it's going to be that bigger case up there. Let me redraw that down here. It's going to look like this. This is angle B, side B, angle A, side A. Well, that'll be C and C. This is 40 feet, 21 feet, and 29 degrees. So obviously we can find angle B now because we have the 21 feet over the sine, 29 degrees. That's our angle and its opposite side that we have. Over the 40 feet is the length of a side that goes on top, because our 21 feet is also the length of a side. Over the sine is angle B up here, sine of angle B. So once again, once we cross multiply and divide, we're not going to find the angle B, we're going to find the sine of the angle B. So let's cross multiply and divide. Sine of 29. Make sure we close that parentheses, times 40 divided by 21. Gives us the sine of B is 0.9234. Again, notice I did not clear out my calculator. I'm leaving it in the calculator because I still have to calculate B, which will be the inverse sine of 0.9234. So we do second sine, 0.9234. Gives us 67.43 degrees. So angle B, 67.43 degrees. And now I can find angle C, once again using that angle sum. 180 minus 29 is 151. Minus 67.43 degrees is 83.57 degrees, I believe. So 83.57. So I drew it a little bit off, but you get the picture. Side C is now found again by using our law of sines. 21 feet over the sine of 29 degrees equals side C over the sine of 83.57. 83.57 degrees. And we'll cross multiply and divide. 21 times the sine of 83.57 divided by the sine of 29 degrees gives me a length of 43.04. Now this does make sense because C does turn out to be the largest of all three of the angles. Its opposite side is the largest. 29 is the smallest of the angles. Its opposite side is the smallest. So this was the case where we were told that B was acute. Given that same information, but being told that B is obtuse, picture would look something like this. This is A, B, and C. This is the 29 degrees. This is little b of 40 feet, little a of 21 feet, and little c over here. Our first step is going to be exactly the same as it was before. We had the 21 feet for A over sine of the 29 degrees for angle A equals the 40 feet for B over the sine of angle B. And when we cross multiply and divide, we're going to get the sine of B again. The sine of 29 degrees, close parentheses, times 40 divided by 21 gives 0.9234. And once again, we're going to do an inverse sine to find angle B. So the inverse sine, second sine of second answer of the 0.9234 is 67.44. Well, that's the answer we got last time, 67.44. We know that's not really angle B because angle B is obtuse. Well, yeah, if we're doing the inverse sine of an obtuse angle, remember from way back up on top from today, there are two angles that have that same sign. There's this angle right here, which is the 67.44. And there's this angle over here that has a reference angle of 67.44. But its actual angle, this one here, is the supplement. So we're going to take 180 degrees minus the 67.44, giving us 112.56 degrees. That is angle B now. So now to find C, we're going to do the exact same thing, 180 degrees minus the 29 degrees, that's still 151 degrees, minus 112.56 degrees. That's going to be 38.44 degrees for angle C. And to find side C, we're going to do the same thing. C is going to be much smaller now because it's opposite a smaller angle, but it's still going to be the 21 over the sine of 29 degrees equals C This time will be over the sine of 38.44 degrees. 21 times the sine of 38.44. Make sure you close that parentheses. Divided by the sine of 29. 26.93. Which makes sense because now angle C is between angles A and B in size. Side C is between sides A and B in size. So that makes sense. So this is a huge source of mistakes for people. Whenever we have two angles and the opposite side, but the opposite side is the shorter side of the two, we need to know if that second angle, the angle that's opposite that second side, we need to know if it's acute or obtuse. If it's obtuse, if we're looking for an obtuse angle, we have to remember that once we do the inverse sine and get the angle, what we really want is the supplement of that angle, 180 degrees minus that angle. Several of you will get this wrong on a test. Now, I'm hoping I'm wrong, but every year there is a large number of people out of the group that when we get that obtuse angle on the test, they forget to subtract it from 180 degrees or to get the supplement. Be very careful with that. There's a fourth possibility with two sides and one angle. And we saw the first one where we had two sides and the angle in between them so that we couldn't use the law of sines at all. We'll use the law of cosines for that. We saw the one where the two sides and the angle across from one of the sides, and we had to know if that opposite side was the shorter of the two sides. We had to know if our second angle opposite the second side was obtuse or acute. The third possibility is we still have two sides and the opposite angle and one angle opposite them. And the side that's opposite our angle is still the smaller of the two sides. But in this case, we will not need to know whether B is acute or obtuse, and let me show you why. So do triangle ABC, little a, little b, little c. So here we know that A is 31 degrees. Little a, side A is 24 feet, and side B is 51 feet. When we go to set this up, we've got the pair, angle A and side A, where we know both the angle and the side. So put the 24 feet over the sine of the 31 degrees. The only other piece of information we have is the 51-foot side for angle B, so that has to go on top as our side length. It is opposite angle B, so it's going to be over the sine of B. So we'll cross multiply and divide. The sine of 31 times 51 divided by 24. We get 1.0945. Now I'm going to go ahead and do it even though I know there's going to be an issue here. If I try to do the inverse sine of 1.0945, my calculator, and any calculator, is going to give you an error. Why? Well, because the sine can never be larger than 1. What's happening here is that this is not a triangle. It doesn't close. This side over here of 24 feet is not long enough to reach back down if I have that 31-degree angle there. So no matter what direction I put that side in, it's never going to reach back to side B. So this does not form a triangle. So that is the other possibility you have to worry about if we are given two sides and one of the angles opposite one of those two sides. The only time it's an issue is when the side that's opposite the given angle is the shorter of the two sides. And there's all sorts of things that can go wrong. We can either be not a triangle, or we have to know whether our second angle is obtuse or acute. Final case. Is where we're given all three sides. So we might be told we got angles A, B, and C, side little a, little b, little c. I might tell you that side C is 58 feet, side B is 34 feet, and side C is 41 feet. We can find these missing angles, but not with the law of sines. Once again, this will use the law of cosines. So we will learn the law of cosines on Monday. We will review how to do these problems, these law of sine problems, on Monday as well. There's a lot of possibilities here, so I realize we might have to go through them a second time. We'll look at law of cosines on Monday. And then I might mention, everybody's like, well, there's a law of sines and a law of cosines. Is there a law of tangents? And the answer is yes, there is. There is a law of tangents. We'll take a brief look at it. If we don't get time Monday or Tuesday, we'll come back the week after Easter and we'll take a peek at it, just so you know. Next week, we are hoping to finish up this unit, which means next Thursday, what is that? Is that April 1st, I believe? It is April 1st. Is our unit test. As all of our unit tests, I will log in. I will see if anybody has any questions. If nobody has any questions, we'll just let you work on your test. As long as your test is done by the end of that day, we'll be good. I did that timing on purpose so that you guys, I'll post the test earlier in the week, so if you guys want to finish your test and be done early for Easter, you guys can. As long as the test is done by the end of the day, Thursday next week. I'll probably post it Monday or Tuesday next week. I don't want to get it out there too soon before we've had the law of cosines under our belt. For now, homework. I always feel like I'm giving a huge amount of homework in this class, but because all of our classes are either a 1.5 hour or 2 hours, it's almost always 2 topics per class. Out of the big book. You have page 775. Oops, sorry. These pages have changed. New edition. 901 to 902. Exercise 36-2, the odds. Page 905, exercise 36-3. Page 908 to 909, exercise 36-5A. And page 912 through 914. Exercise 36-5B. So you'll have the rest of our time to start working on those. I'll be on the network here for a little while. If you have any questions, feel free to ask. Otherwise, you guys have a great week.